Well, good to see everybody. Hope you all had a restful respite last week. Thanks for tuning back into our weekly Science Talk series. We are focusing on UN Research Thrust B, which explores the impacts of innovative technological solutions for urban water systems. We do have 3 more consecutive weeks of webinars leading up to winter break, so please be sure to tune in the next 2 weeks as we explore flood risks to assets and gray water reuse. As you all know, we are recording the webinars and I post those to our YouTube channel and the UN website. Feel free to use the chat queue or turn your mic and or webcam on for an engaging discussion with Brian at the end of his presentation. So with that, I am excited to introduce today Dr. Brian Bledsoe, professor in resilient infrastructure at the University of Georgia. Dr. Bledsoe has 25 years of experience as an engineer, hydrologist, and environmental scientist in the private and public sectors. Before entering the professorate, he worked in the private sector as a consulting engineer and surveyor, and for the state of North Carolina as a watershed restoration specialist and state nonpoint source program coordinator. Brian's research is focused on the interface of hydrology, ecology, and urban water sustainability with an emphasis on green infrastructure, including streams, floodplains, and stormwater systems. Hopefully that's still accurate.
I'm just older. that was the only inaccuracy there. Yeah. Okay, very good. That's a very generous introduction. Thank you.
I wrote it myself. Just kidding.
All right. Amazing. Doesn't surprise me though, Sarah. You're an intuitive person. So shall I take it away?
Take it away.
Okay. Great. Well, thank you all so much for your interest and for being here today. I'm going to see if I can get the PowerPoint activated here. Okay, are you seeing?
Yep, you are. Looks good. You're ready to go.
Okay, wonderful. Well, what I've got for you today is a mix of things that many of you have already seen, those of you who are part of the UN network, but there's a smattering of late-breaking research and new findings. But I'll forewarn you, I'm going to, kind of wax philosophical a bit at the end and share some, reflections on kind of what we were thinking about when we went into this project, and what I think we're finding. Try to bring together some of the scattered pieces. I want to acknowledge my co-authors, Rod Lammers, who I'm happy to report is now happily situated in Mount Pleasant, Michigan, as a tenure track faculty there at the University of Central Michigan. Haley Seltzer came to us at UGA as an REU student, and now she was working as a master's student at UGA, and now she's decided she wants to go on for a PhD. So there's a wonderful story from the REU program from UN. And Tim Stevens, who's now a high-powered consultant and hydrodynamic modeler. That's the UGA team. Tim finished his PhD. They helped me with these slides. And then Andy Miller and Gina Lee at University of Maryland, Baltimore County, and their excellent work on urban stream dynamics. So start off a little bit with the motivation. I kind of like this cartoon that gets at the vicious cycle of urban flooding, and there are a lot of things that are at play here, and you see the references to zoning and land use decisions and denial and procrastination, but we could also overlay these days, inaccuracies in flood maps, increasing rainfall intensities, more urbanization and impervious area. Our stormwater controls may or may not be effective or maintained and operated properly. And so what I'm getting at today is, some explorations into these social dimensions a little bit, but a lot of opportunities that come with this. Gilbert White, the great geographer, was there in the room when FEMA decided they were going to do 100-year floodplains and have this sort of bright line in the sand with this simplistic definition of, the 1% annual event. Gilbert and the other experts had recommended to the agency that would become FEMA that they actually only do the 100-year as a first little interim baby step, but they actually expand the program and deal with uncertainties and move beyond the 100-year. That still hasn't happened, but there's some promising signals. But suffice it to say that we expect urban flood hazards and the footprint of these floodplains to expand by, roughly 50% in the next few decades. I have some numbers here I wrote down. Property losses, that doesn't include all the, social impacts and health effects and all of those things, which are disproportionate on some vulnerable communities. Those property losses alone exceed $100 billion per decade in the US, and they're going up. And that's sort of the theme of some of these recent publications from ASCE and FEMA, that the urban footprint and changing climate, more intense rainfall are going to interact and expand these floodplains. So there's some opportunities here, and we're going to explore that today. So here's my outline. I'll give you a recap of some of the things we've been doing with probabilistic flood mapping. I'll highlight some of Andy and Gina's work in the Piedmont of Maryland on the dynamics of urban stream restoration projects. Explored, the efficacy of green infrastructure for flood risk reduction. I'll tell you about some local work here in Athens, Georgia, where we've been exploring social vulnerability and which populations are most exposed to flood risks, and some interactions we've had with the city and county, Athens, Clarke County, to see if we could apply some of the research products from UN in making decisions about natural infrastructure as a means of reducing flood risk inequities. And then as I said, I'll try to weave some things together at the end with some reflection. So, we've basically been trying to look at, compounding risks. We know that rainfall is intensifying here in the Southeast US and a lot of other places. The urban footprint is expanding. Here we call it Charlanta. The whole I-85 corridor from Atlanta to Charlotte is rapidly urbanizing the Piedmont Atlantic megalopolis. Can't even say it, it's so scary. Our stormwater systems are evolving, channels are changing. So we've been trying to get at these interactions, understand them better so that we can make some recommendations on stormwater management, floodplain management, and stream restoration, with the ultimate goal of, helping protect people and communities and their livelihoods from climate change impacts through communication. And, ultimately we're looking at green-gray hybrid infrastructure solutions. So in a nutshell, one thing we've worked on is trying to map floodplains where there's not just this bright line in the sand where you say, here is the line, it's a deterministic thing, and you're either in or out, a binary situation. So we basically take some models and HEC-RAS and other tools, and we do this thing called Monte Carlo simulation, where we run the model thousands of times and we turn knobs on the model because as you see over here, we don't really know, for example, what the 100-year discharge, we don't really know for sure what the flow resistance is along the stream in the floodplain. We don't really know what the topography of the channel is going to be and whether it's going to fill in with sediment or enlarge. And so we treat those inputs and parameters as uncertain. We run the simulation model thousands of times, and then we explore that space. And it's like putting a confidence band around the floodplain extent. And in some places, it's not a huge deal because the valley is fairly narrow and entrenched, but in other places that are more flat and you have certain topographic breaks, the uncertainty can be very large in terms of its footprint. So what you end up with are a variety of things, but here's the black line on this map is the traditional FEMA flood insurance rate map, and you can see those little white boxes are houses where they've built right up to that line. And this is still a fairly entrenched valley here. This is McMullen Creek in Charlotte, North Carolina. And so those folks, they looked at the map and they said, yeah, okay, we're well outside the floodplain, but there's still a very high probability of a lot of those folks, even that second row of houses getting flooded in some situations. Now, I want to acknowledge that FEMA and their Risk Map 2 efforts and some of the things that are happening now are very encouraging, as in terms of being more transparent about these sort of fuzzy floodplain lines or confidence bands on these floodplains. And we've talked a lot over the course of UN about how do we communicate floods risks more intuitively or more effectively. For example, if nothing changes with climate and everything is known, the 100-year flood has a 1 in 4 chance of occurring over the next 30 years, about 26%. If you want to have 90% reliability, that if you live on the edge of the floodplain and you want to have 90% reliability over 30 years, you'd have to be out at the fringe of the 285-year flood. And if you wanted that same reliability over 50 years, you would be building your house at the height of the 474-year flood. And that's without climate change or changing imperviousness and urbanization. And so we've explored this with Sharon Harlan and Liz Mack, and Tim Stevens did a lot of this work with them on exploring how to communicate these uncertainties around flood hazards. And, to date, I would say the consensus, my understanding is that folks like to see some sort of contours, and they are more likely to understand a risk over some time horizon, like 20 or 30 years, as opposed to telling them something is a 100-year flood or a 1% annual exceedance. So there's a lot more work to be done here. One thing is clear: people do not understand the concept of the 100-year or 1% annual exceedance event very well. So a lot to do there. But we've been trying to make these maps in different ways to express reliability, the likelihood that these floods won't happen over a certain time horizon. And then we can connect those same concepts to things like, is it ankle deep, knee deep, waist deep? Is it fast enough to, sweep away a car or a child? Of course, you need to get into higher resolution modeling, two-dimensional modeling for those kinds of predictions to do that reasonably well. And I would offer, that there are a few papers out there on this, and with Tim Stevens as the lead on some of the probabilistic mapping stuff, and some philosophical things about, a more humility-based approach to flood risk management. Now, the late-breaking research here is Tim Stevens' work on reliability, and a little tongue-in-cheek here, how reliable is reliability? The idea of reliability. Reliability is just the probability that the bad thing is not going to happen in some time frame. So, like in that top equation, 0.01 would be the probability in any given year of the 100-year flood. And then you could put n equals 30 in there, and you would get, 74%. Okay, but as far as we know, nobody's ever really worked out the mathematics fully of how to do the uncertainty in the reliability in a non-stationary climate where the probability of the flood is changing over time. So, for example, the 100-year flood may be the 80-year flood 5 years from now, and then 15 years from now it's the 60-year flood. And so Tim has worked out the mathematics of this, and this is the paper that's going in right now, is defining these probability distributions of reliability. And this all sounds kind of esoteric maybe, but it's an interesting thing to think about. If you're one of these houses that live right here on the edge, and somebody says, well, how reliable do you want this to be? Well, you could say, okay, the 100-year will give you 76% reliability over 30 years. But that's without climate change. And that's without accounting for the fact that that's going to be wrong at about half the houses. So most people don't think about it that way. They think about, well, they're telling me this is where the line is, and that's true, for every house. How would they feel about it if you said, but this is only accurate for about half the houses, and about the other half, it's going to be worse than that. So there's a lot to do here in terms of translating these confidence bands on reliability into things that are for public consumption, let's say, to advance management and practice. But I think it's pretty exciting what Tim has done here. So to kind of summarize this, these uncertainties vary a lot in space and time. We found that, for example, the way bridges are handled in hydraulic models to predict floodplains and flood hazards have a huge impact on this uncertainty. And so, the changing channels, the changing land use, the changing precipitation, all of those things are coming together to expand those confidence bands around the flood hazard zones. There are ways of communicating this that are more understandable than others, and we'll continue to work on that. We think this is useful because it can help us identify where these hidden flood risks are, and again, help with communication. But I really want to underscore that last point there, that I think these probabilistic maps showing that larger footprint of risk and these flood hazard zones can be sort of a template for thinking about other opportunities like greenways, stream restoration, bike paths. Think about the Infrastructure Act that just passed, all the things that could be done with this information of knowing where these previously hidden risks and vulnerabilities are. And these could deliver a lot of other benefits besides just flood risk reduction, obviously. So let's look at Andy Miller and Gina Lee's stuff for a little bit here. Really their work ties to this big picture because we're trying to understand how urban streams respond to changing climate, changing land use. What is the feasibility of restoring streams in these hyper urban environments, and especially in Maryland, the Piedmont of Maryland, some of the flashiest streams on the face of the earth. And Gina and Andy are doing some really innovative things with their hydraulic modeling and the monitoring that they're doing of these streams as they change over time. Urban fluvial geomorphology is like fluvial geomorphology on steroids. I mean, you could see stuff happening over a few years that would take a long time in other places. So it's fascinating stuff. Here's one example: Mine Bank Run. They call the creeks runs in this part of the world. Lots of urbanization, a lot of it uncontrolled. There was a stream restoration project done there where that little white box is, and we're going to look at what happened. So here's the restoration project went in. They built some nice little riffles and stuff here. So far, so good. And then lots of flashy peak flows come along, and you can see point bar formation, meandering sinuosity starting to develop. The channel is not just migrating laterally, which is not inherently a bad thing. Maybe if you own this house here, you think it is. But the channel is also enlarging and downcutting. And so there, over a matter of a few years, what's that, 16 years or so, you can see the high banks here and all the changes that have happened. And so Gina and Andy are tracking these changes with LIDAR and hydraulic modeling, trying to understand these processes. Here's an example of some of the hydraulic modeling using two-flow and HEC-RAS, and they're kind of understanding the shear stresses and the stream powers that are associated with these different responses. So the things we just went through, they're understanding the velocity and shear stress fields as those channels evolve. And when they go out there and do the structure from motion, they can get very high resolution topography to help them build these models. And so why is this happening? Is it because people didn't build the project right, or what? But there's a lot going on here, but basically what this slide shows is that from about 2000 to 2020, over 2 decades, there was a very substantial increase in the frequency of peak flows, which coincided with an increase in extreme rainfall. So these are 5-year moving averages of exceedance frequencies, with the peak flows in blue and the rainfall in red. So the bottom line is that these channels it's not just the urbanization. The urbanization is interacting with an amplified rainfall regime, and you know, these small watersheds like these that we're looking at here, you know, on the order of, let's say, 10 square kilometers, you know, 1 to 100 square kilometers, but maybe 10 as an order of magnitude, they are extremely susceptible, and stream restoration, you know, is a really formidable challenge in these basins. You know, another thing of interest here that Andy and Gina have uncovered is that, you know, for example, in these urban watersheds in Maryland that vary, if you look here in the yellow, this is what percentage of the basin drains to stormwater management. And so almost none, you know, 30 something percent, or, you know, 60% drains to stormwater management. They're really not seeing much of a difference between the ones that have stormwater management and the ones that don't. And, you know, part of that could be the vintage of the stormwater management and the type, but it's partly or mostly just the stormwater controls being overwhelmed with this super intense rainfall. It also underscores something that we're working on, I'm not talking about today, and Jim Smith's on the line, and he knows more about this than I do, but you know, the need to update our intensity, duration, frequency curves that we use for designing urban infrastructure, including stormwater. And you can see here the correlation between the increases in precipitation and peak flow and the basin that's got a lot of stormwater control. The black dots here, DR1, is really just part of, you know, that same cloud of points. So, okay, so to summarize, you know, I didn't really show evidence of it, but, you know, we are seeing evidence that stream restoration can reduce urban flooding, but the outcomes are variable, and it's really complicated in terms of dealing with the flashiness and the increasing rainfall intensities and so on, in terms of incorporating that into stream restoration designs. And there's not a lot of evidence that the stormwater controls that are currently in place are doing a whole lot to mitigate that. And I've already touched on the IDF curves. Okay, let's talk briefly about some work that's more recent on green infrastructure and how effective it is for reducing flood volumes and peaks in different climates, and think a little bit about how that interacts with stream restoration. So everybody knows what green infrastructure is these days, and, you know, as opposed to being random acts of kindness and little postage stamps around the city, you know, these things can be coordinated into an integrated system that works together. And we can explore those kinds of spatial configurations in our hydrologic models. We've focused a lot on hydrologic modeling with bioretention areas and permeable pavements, and taking, you know, real watersheds and converting impervious areas to those kinds of green infrastructure practices. Using different hydrologic models, ranging from SWIM to Kinneros 2 and Geisha. But the results I'm going to show you today are from the stormwater management model, the EPA SWIM model. So there's a watershed that in Ohio, Shaler's crossing. It's not too far from Cincinnati, and you know, the folks at EPA in Cincinnati have worked a lot on this watershed with really high resolution LiDAR and information on land use. And these are just little pictures of the Shalers Crossing watershed to give you a sense of the scale, where this is, you know, a kilometer is, you know, 4 of these boxes here. So it's a pretty small watershed, but it's handy for exploring some of these questions. And we want to know, you know, what can strategically placed green water infrastructure do at this watershed scale in terms of, again, peak flow reduction, volume reduction? When does it get overwhelmed? What kind of rainfall events in different climates overwhelm it? And, you know, in terms of just a general concept, you know, what we see here is that you know, depending on how we run our simulations with parameter uncertainty and all that, you know, first off, we get a lot of variability. But if we just look at the sort of mean response here, these dots, you know, we see diminishing returns out here beyond, you know, the 5-year rainfall event. And so, you know, as you would sort of guess intuitively, at some point the sponge just can't hold any more water. It's already saturated and soaked. And so we're trying to get a handle on, you know, what are realistic expectations for the performance of green infrastructure. So in terms of, you know, capturing volumes and reducing discharges, we do see these diminishing returns. And this is just with the climate there in Ohio locally. And, you know, in terms of the benefits of the houses that are in the effects on the houses that are in the floodplain, it's also pretty variable. But, you know, again, in this scenario, beyond about the 5-year event, we don't see a lot of benefit. That's not to say green infrastructure is lousy. I'm not saying that at all. It can really help us with flood risk reduction for these more frequent events, while delivering all kinds of other benefits like cooling the city and the neighborhood and improving water quality, etc. But what I'm going to show you now is what happens if we take that watershed and we impose different rainfall regimes. 8 odd, and you see some of the representative cities here from Seattle. Uh-oh, looks like my internet is unstable. Sorry, I just got a notice that my internet is unstable. I hope I'm...
You cut out for just a second, but I can hear and see you just fine, Brian.
Okay, sorry about that. So 8 climatic regions, you know, from Tampa and New Orleans and Atlanta up to Seattle and Elko, Nevada, and Los Angeles, and so on. And basically what we did is we imposed the rainfall regimes from these different regions on the Shalers Crossing watershed with different configurations of green infrastructure. And this is super busy. I apologize for that, but I would say, you know, the things to look at here are, you know, across the top, if you can see this, peak flow reduction, you know, irrespective of the infiltration capacity, you know, the high infiltration capacity green infrastructure, you know, in terms of cranking the knobs on hydraulic conductivity and that kind of thing, it certainly has an effect. But once we get out beyond about, you know, 3 or 4 inches of rainfall, we really see the capacity of a typical bioretention area, permeable paver kind of practice. It really drops off. as you can maybe see here at the bottom, we're exploring different drainage area ratios. And what that means is how much of what proportion of what's the size of the green infrastructure relative to the upstream impervious area draining into it. So, you know, the bottom line on the volume runoff, this is runoff volume here, is that again, we get out here at about 3 or 4 inches of rainfall, 10, 15 centimeters, and everything just kind of starts to asymptote here. Now, one interesting phenomenon that we observed here is that, you know, this is again is all the regions, trying these different regions. If we look at peak flow reduction and we divide it into watershed, entire watershed effects versus sub-basin effects, you know, like here's the watershed again, and we have little sub-basins inside of this watershed. So depending on whether we look at the whole thing or the sub-basins individually within there, we see different things. So if we look at peak flows, we see that the benefits are greater and more discernible at the watershed scale than at the sub-basin scale. On the other hand, conversely, if we look at runoff volume, we see that the sub-basin effects are much more detectable. The effects at the sub-basin scale are much more detectable than at the watershed scale. And we attribute this to the fact that at the watershed scale, the green infrastructure desynchronized the peak flows. And this was kind of a surprise to us because we didn't intentionally place the green infrastructure in a way that was designed to desynchronize, but it happened anyway. And so this is an area for further research. You know, I always say, you know, people say when in doubt, build it stout, but I always say, you know, when in doubt, spread it out in space and in time. And that's what has happened here with this green infrastructure. So that's another, if you are strategic with it at the basin scale, you may be able to achieve some of these desynchronization benefits. Okay, moving along here, let's talk for a minute about how this might connect with stream restoration. I've always thought that, you know, I've seen in practice that these things are done sort of in silos. You know, the people who are working on stormwater management are often not the same people who are doing stream restoration. And so a lot of times streams are blowing out and eroding because of upstream urbanization. Wouldn't it be great if we could sort of coordinate stormwater, the placement of stormwater controls with our plans for stream restoration? So Rod Lammers and also Tyler Dale at CSU did some great modeling work, again, with the stormwater management model and with Rod's river erosion model, REM, to explore this question of what do we get in terms of erosion and phosphorus loading in this urban watershed in Colorado, the Front Range. This is Big Dry Creek, which if you go, you know, north on from Denver towards Fort Collins and you cross 104th Avenue, you go across the golf course there, that's Big Dry Creek. And so what Rod and Tyler did was they coupled the swim model with the morphodynamic model, the river erosion model that tells you about incision and bank failure and transport of phosphorus that's attached to the sediments in the bank. You know, this particular stream has total phosphorus concentrations, you know, between 100 and 1,000 parts per million, depending on how much clay is in the bank. And so when the bank erodes, phosphorus goes with hitchhiking with the sediment. And so long story short, you know, here's the river erosion model where we're hitting it with these different stormwater green infrastructure and detention basin scenarios. And it's telling us, you know, how the river channel responds and where we might want to put our stream restoration. And this is all published in Journal of Environmental Quality if you want to check it out. But you know, get the vertical degradation, the mass wasting, and bank failures. And so what we found is that if we don't coordinate stormwater management with our stream restoration activities, we get a certain phosphorus loading downstream. And if we do it randomly versus coordinated, it does reduce phosphorus. Well, sorry, I misspoke. This is when you just do restoration in either no restoration, sort of random, opportunistic, ad hoc stream restoration, or you're coordinating it with the stormwater management. So if are coordinating it with other projects in the basin, and then if you coordinate the stream restoration and the stormwater management, you get significantly reduced phosphorus and sediment export. And we tried a lot of different variations in this model simulation framework. And, you know, it was a pretty robust result. And so what I'm trying to say here is that, you know, there is some pretty compelling evidence that if we were able to overcome some of the bureaucratic obstacles and silos to coordinate our stormwater management with our restoration, stream restoration. And it, by the way, it's a lot easier to restore these kinds of snowmelt streams than those in Maryland. That's a story for another day. You know, we could do a lot of good things if the stormwater people were talking to the stream people. And some of these ideas have been expressed in some reports for the Water Environment Research Foundation, or now they're just Water Research Foundation, right? And how do you calculate water quality credits for stream restoration, sort of in a stormwater context? Okay, just wrapping up here and moving right along. We've been working with Athens Clarke County. That's where UGA is situated, in the classic city of Athens, Dr. Smith's old stomping grounds here. And basically what we've found is through, you know, our probabilistic floodplain modeling and combining the flood insurance rate maps with other modeling approaches. Bottom line, there's a lot of flood risk and flood exposure outside the sort of jurisdictional or regulatory 100-year flood zone. And it really doesn't matter whether we throw climate change in there or not. We see these flood hazard zones that extend far outside the FEMA mapped zone. And this is no surprise, right? Because so many of the flood insurance claims come from outside the regulatory floodplain. But this is Haley Seltzer's work. And as I mentioned, Haley was an REU student with us through UWIN, and that translated into her entering the master's program here at UGA. And now she's decided she wants to transition into the PhD program, which I'm delighted about, and she's doing some really exciting work on looking at flood risk inequities and the demographics of who's exposed to flooding. And so Haley's been looking at flood risks relative to census data, and where's the existing greenway network here in Athens, Clarke County. That's what ACC is, the Consolidated Government of Athens, Clarke County. So she's combining parcel scale flood risk data with demographic data from the census, using some dasometric methods developed by Neil Debbage and Marshall Shepard, and basically overlaying those in various ways, trying to understand the likelihood, what are the average demographics of flood exposure, and then what are the exposures for low income Black and Hispanic citizens in these census tracts. And basically what Haley has shown in this initial analysis is that these relative risk ratios are really amplified for Black, Hispanic, and low-income folks here in Athens, Clarke County. This has been shown in a lot of other places, like Neil Debbage's work. In some cases, the risk ratios were almost 3 times as high. And what that means, a risk ratio, is the likelihood that somebody is in a flood hazard zone based on their demographics compared to the average across all the demographics. And so that would mean, over here, the Black citizens in these census tracts have almost a 3 times higher likelihood of being in the flood hazard zone than the average person. And so we basically are exploring this relative to natural infrastructure solutions, stream restoration, floodplain management solutions that can help reduce some of these risk inequities. We took this to the Athens Greenway Commission. But before I tell you about that, I'll show you this one slide. This is some late breaking research from Haley, and these numbers correspond to different census tracts. But basically, what Haley is showing here is that if you have the 20-year flood, 40-year flood, well, actually 20, 50-year, 100-year flood here on this axis, and you have a measure of inequity here per census tract, what you see essentially is that each census tract has its own signature in terms of which floods people are most exposed to. So in these blue ones and this orange one, it's the more frequent floods that folks have the relatively high exposure to. So this is the message that we took to, we were asked to present some of this at the Greenway Commission meeting in Athens, and I think the county manager was there, and we these were the bullet points that we delivered to them, that we're seeing these increasing rainfall intensities. There are risk inequities in Athens, Clarke County, and these probabilistic maps and these analyses of relative risk can inform your planning for flood risk reduction interventions that can also nudge the needle towards more equity in flood risk exposure. And we also told them, we need riparian buffers that extend well outside the FEMA regulatory floodplain. So to just wrap it up here, I'll go through this really quick. you know, we're thinking a lot about infrastructure and natural infrastructure, but ultimately, you know, with flood resilience and urban resilience in general, I think it is useful to think across these so-called 6 capitals of community resilience. And this is something that the National Academies is talking about a lot right now. And, you know, when Mazdak and I and Sybil and others started thinking about the UN project initially, you know, I was inspired by this idea that urban floodplain corridors could be a vehicle for building flood resilience through uh, stream restoration, through mobility. Renaturing cities could ultimately deliver lots of social benefits. We all know the triple bottom line here, right? But even happiness and health. And so, you know, happiness is wired into Americans' worldview. And I would ask, but what, you know, people might say, well, what does happiness have to do with floodplains and streams and stormwater? I would argue there is a role for natural infrastructure to help people be happier and healthier. And there's a growing literature that supports this. And we see it playing out in places like Greenville, South Carolina here on the top, and Atlanta, Georgia on the bottom. Here's Sawmill River in New York, even these incredibly urbanized environments like this one in Korea. And it's clear that people hate commutes and they love, you know, in cars. They hate commutes in cars. They need third places outside of work and outside the home for regeneration, rejuvenation, recreation. Fort Collins is a stellar model of how urban river parkways can deliver impressive flood management benefits and also a whole host of other social benefits, including health. You know, the public health folks tell us $3 to $10 in direct medical benefit for every dollar you put into stream restoration. So I am still inspired by this idea that was there at the outset of UN, that we can take places that look like this and help them become more like this as part of our flood management programs. And, you know, just sort of conclusions here, wrapping it up. I think, you know, all of these things can come together. The probabilistic corridors and better understanding and communication of flood risks, understanding those inequities, aligning flood protection and resilience planning with people's, you know, real understanding of risk and their vulnerabilities, coordinating the stormwater and the stream restoration, etc. It's about breaking down silos. So I think we need to seek integration of floodplain management, stormwater, stream restoration. You know, it's not just in the parks department, the utilities department, the natural areas department. It's all got to come together for this full array of benefits. And I think we are making progress. So I hope you all won't get discouraged. So we started out with this question, you know, can these rambunctious, renatured floodplains help with flood resiliency, clean up the water, cool the city, give people mobility opportunities, improve their health and happiness? I say yes. And I wanted to say, when I lived in Fort Collins and I rode along Spring Creek here to go to Dairy Queen and eat an ice cream, I was very happy. Okay, that's all. Thank you. And I'd be happy to address any questions. Looks like I ran long, but we've got 4 minutes or so, maybe, if anybody's still interested in chatting.
Great. Thanks, Brian. Dairy Queen's still there, by the way. It looks a whole lot different around there now, though.
Yeah, it's a great place. What
Alan, got a
questions do folks have?
I have a quick question. So if the GI can't really help with the big stuff, which is I think one of the things that you found, right? Like is there a way to design it so that it doesn't get trashed by the big stuff? Because there's all this extra money and effort to establish it and to make it beautiful and all that, and if it just gets trashed by the big flows, are we effects?
Right. It's great to see you, Alan. I would say, I'm not trying to say that it doesn't help and it gets trashed. I think I would, phrase it a little differently. I would say it can only do so much. It can help, but it has limits. And I think, it can bounce back from those events. It gets overwhelmed. And so what we have to do is figure out ways for the conventional solutions, the gray solutions, to work together with the greening. But I think they all, right now, there's not a lot of coordination between the two, so there's a lot of opportunities there. But yeah, sometimes you just can't get any more water in the ground to soak in, so you've got to create surface storage or dig tunnels under the ground or some kind of bucket to capture it in.
Brian, following up on that, from the remnants of Ida, from DC up to New York City, the flooding was extreme short duration rainfall. It was stormwater systems that were overwhelmed. From DC up to New York City, the fatalities were in at-risk communities. My sense is that the way people are thinking about attacking this, not just from Ida, but in light of the sequence of just major flood episodes, is major capital projects. The stormwater system is just under capacity, and the only way to deal with it is spending large dollars. If that's the way things are going, is there is there a way of tacking on other things, given that you're going to see these massive capital projects taking place in our old cities?
Yeah, and I think there are ways to blend them together, and the Infrastructure Act that just passed challenges us to do that. Natural infrastructure is mentioned in there upwards of 17 times, and it explicitly says that we have to look at those nature-based solutions as part of these large civil works projects. So there's a lot of work to be done to do those projects, do the right projects the right way. Where we really do integrate the green and the gray.
Good.
Great. Any other questions? So would we call that like a sage approach? If you mix the colors green and gray together, that would give you like sage.
Sure.
I'm throwing that out there in the world for someone to use on their next, NSF proposal, the sage approach.
That's very good branding.
I do my best. All right, well, we are 1 minute past the hour. I wish you all a wonderful afternoon and hope to see everybody next week. Thanks for your time. Good to see you all.
Good to see you.
Take
Thanks
care.
for coming. Yeah,
Bye.
appreciate it. Bye.